Welcome everyone for this online introductory course on representation theory of finite groups. In this course, I will introduce the representation theory via studying finite dimensional representations of finite groups. So, we will begin with reviewing some basic linear algebra. So, if you are very familiar with linear algebra, then you can skip 2 or 3 lectures. Okay, let us start. So, our base field will be complex numbers throughout this course. We will assume that all vector spaces are defined over complex numbers. So, let us denote C by complex numbers. So, this is our base field. So, that means all vector spaces are defined over complex numbers. So, mostly we will focus on finite dimensional representations. So, that means all vector spaces will be assumed to be finite dimensional unless otherwise stated. So, let us start with finite dimensional vector space. Let us call it capital V. So, V is finite dimensional vector space defined over complex numbers, and let us say B is the basis of this capital V. So, B, which is consisting of n number of vectors, where n is the dimension of V. So, this is given basis of V. So, then with respect to this basis, we can talk about the coordinates of any given vector. So, for any vector V in V, so we can write this V as a linear combination of these basis vectors in a unique way. So, let us say we have this unique coordinates B1 etc. Bn from Cn such that this V is written as B1 V1 plus etc. plus Bn Vn. So, these Bi's consisting of n tuple, so that is called the coordinate of this V with respect to the basis B. So, which is denoted by the bracket Vb, so which is the n tuple of these complex numbers. So, this is called the coordinate of V with respect to the basis capital V. So, now this indeed defines a map from V to Cn. So, that is the coordinate function. So, let us use pi b to denote that function. So, we have this pi b, which is a function from V to Cn given by given vector, you just send it to the coordinate vector of that vector with respect to B. And it is easy to verify this is indeed a vector space isomorphism. So, this is an vector space isomorphism. So, now if we change the basis, then this coordinates also will get changed. So, we want to understand how these coordinates with respect to two different bases are actually related. So, for which we need to talk about the change of basis. So, we will come to that a little later. So, first I will record some equivalent definition of basis. So, this is an exercise. I will leave it to you because this is some basic fact from linear algebra. So, we start with the finite dimensional vector space V over C. So, let us say V is finite dimensional vector space over C, So, with the dimension let us say n. So, then the following statements are equivalent. So, then the following statements are equivalent. The very first statement, the set B, which is being a basis. So, recall that basis means it must be linearly independent and it should span the vector space V. So, it is linearly independent plus spanning set. The second equivalent definition, it is a maximal linearly independent subset of V. So, B is a maximal linearly independent subset of V. The third equivalent definition, it is also a minimal spanning subset of V. So, B is a minimal spanning subset of V. So, we can also use the map pi b and then say that one of the equivalent condition will be the pi b is an isomorphism. So, that means for each vector v we have these unique coordinates b 1 etcetera b n. So, let me just write it here. So, for each v in capital V, there exist unique b 1 etcetera b n from C n such that V can be written as linear combination of those V i's. So, b 1 v 1 plus etcetera plus b n v n. Okay. So, this is some basic result that I assume everyone knows from linear algebra. So, now let us talk about the matrix of a linear map with respect to some basis. So, since we want to consider general linear transformation, so we actually take two different vector spaces. So, let us fix two vector spaces, call it V and W. So, these are two 5-dimensional vector spaces over complex numbers. Assume that the dimension of V is n and then the dimension of W is m. So, now we can fix bases. So, B let us call it V 1 etcetera V n is a basis of capital V and then B dash let us call it W 1 etcetera W m. So, this is a basis of W. So, now let us say we are given a linear transformation T from V to W. So, this is a C linear map or transformation. So, now we want to talk about the matrix of T with respect to these bases. So, for which we need to actually write down how T V j looks like in terms of the basis B dash. So, let us just write down that. So, T V j, so it can be written as linear combination of the basis elements in B dash which are W i's. So, then this you can write it as linear combination of A I j W I, where I range from 1 to m. So, for each j 1 to m 1 to n, so we are able to write this. So, now the matrix of T with respect to these bases, so they are nothing but these coefficients A I j, which you record it as matrix. So, the matrix of T with respect to B and B dash, which is just defined to be these coefficients A I j. So, which is m by n matrix, and you can see that. So, this matrix representation possesses all the information about the linear transformation T. So, we also use simply this simplified notation T b if V equal to W and B equal to B dash. So, this is called the matrix of T or the matrix representation of T with respect to the bases B and B dash. The matrix of T with respect to the bases B and B dash. Okay. So, what is the importance of this matrix representation? So, once we fix the basis of V and W, then we have this natural isomorphism of home space and this the set of all m by n matrices. So, let us just recall that. So, we can define this isomorphism, let us call it pi b b dash, which is from this home space, which is set of all C linear maps from V to W. So, this is the set of all C linear maps from V to W from this home space to the matrix space, which consisting of the set of all m by n matrices over complex numbers. So, this is the set of all m by n matrices over complex numbers. So, we have this isomorphism which is given by given T, you just send it to the matrix representation of T with respect to these spaces, and this is an isomorphism, and that is easy to prove. I will leave it to you. So, now with this we also use the following notations. So, we denote this home space from V to V as the endomorphism of V. So, we call it this end of V. So, this is the notation used, and whenever we actually talk about invertible linear operators, we denote it by GL of V. So, this is the set of all invertible linear operators. So, once we fix a basis of V, then it is easy to actually prove that. So, the GL of V naturally isomorphic to GL of Cn. So, which is again denoted by GL and C. So, we use this simplified notation GL and C to denote the set of all invertible n by n matrices. So, let us actually see some properties of this matrix representation. So, the matrix representation is very important. It actually, like I said, possesses all the information about the linear transformations. So, now let us actually understand some basic properties of the matrix representations. So, the most important thing is the change of basis. So, for that, so we need to actually first understand what happens if we actually compose two linear transformations. So, for that let us actually take 3 spaces instead of 2, because we want to talk about composition of linear maps. So, let us take U, V, W to be linear spaces. So, let us assume they are finite dimensional vector spaces defined over complex numbers. So, we also assume the dimension of U to be M. So, let us use this notation. Dimension of V we denote by N, let us keep that notation, and then dimension of W to be m. So, the dimension of u we can denote it by p. Okay. So, now we fix basis of u v w. So, let us call A is the basis of u, V is basis of the basis of V to be B and the basis of W to be C. So, now let us say we have a linear transformation defined from u to V and then V to W. So, from u to V we have the linear transformation T 1 and then V to W we have another linear transformation T 2. So, then by composing them we get the linear transformation T 2 composition T 1. So, now we want to actually understand the matrix representation of T 2 composition T 1 in terms of the matrix representations of T 2 and T 1. Indeed, we can prove that the matrix representation of T 2 composition T 1. So, here recall the bases are here A, here B, here C. So, these are the bases. So, if we actually work with this basis, so then we get the matrix representation of T 2 composition T 1 is nothing but the product of the matrix representation of T 2 and T 1. So, here with respect to B C, here with respect to A B. So, this is indeed not very difficult to prove. I will just outline the proof. So, then one can actually work it out. Okay. In order to actually understand this equality, so first let us understand the coordinates with respect to this basis when we apply linear transformation. So, let us start with one operator and then try to understand what happens to the coordinates of the image vectors. So, let us take T be a map from V to W and then let us fix B to be basis of this V and then C to be basis of W. So, these are the bases. So, now let us write down explicitly B to be V 1 etcetera V n and then C to be W 1 etcetera W n. Now, with respect to these bases we want to write down the coordinates. So, let us look at the coordinates of the image T v with respect to C, where let us say V is given by B 1 V 1 plus etcetera plus B n V n. So, then that means T v is nothing but B 1 T v 1 plus etcetera plus B n T v n. So, now recall the way we have defined the matrix of T. So, then T v j becomes equal to summation A I j W I range from 1 to m. So, if we use this, so then it is clear that T v becomes equal to summation B j T v j range from 1 to n. So, which is equal to summation B j summation A I j W I range from 1 to m, j range from 1 to n. So, by changing these summations we easily get T v equal to summation I range from 1 to m summation B j A I j W I. So, that means, so the matrix of T with respect to the basis B C that plays a role in the coordinates of T v. So, let us understand what this coefficient represents. So, if we consider the matrix of T with respect to this basis, so it looks like A11, A12 etc., A1n, and then so the ith row will be AI1, AI2 etc., AIN. So, then if you just multiply this with the coordinate vectors of V, so then you can see that the ith component here is going to be summation Bj Aij. So, which is the coefficient here that we have. So, that means, so this part is nothing but coming from this matrix multiplication, the matrix of T times this coordinate vector of V. So, that means this coordinates of this TV equal to, you take the matrix of T with respect to BC and then multiply by the coordinates of V with respect to B. Okay. So, this is some simple calculation that tells you that the relationship between the coordinates and this matrix representation of T. Okay. So, now you can actually easily prove this fact. Okay. So, it is now very easy. Okay. Maybe let me just do it here. So, what we can do, we can start with some vector u in u. Okay. So, for any u in u, so recall that you have this u2v T1 and then v2w T2. So, then you want to understand the composition in terms of T1 and T2. Okay. So, we are interested in the matrix representation of this T2 composition T1. So, in order to compute that, what we will do, we just compute the coordinate of the image of this vector u. So, you take T2 composition T1 and then apply u. So, then by definition this is nothing but T2 of T1 of u. So, now if you use the relationship between the coordinate of the image and the matrix representation of T, so then you can easily rewrite this equation as follows. So, we just compute the coordinates of the image with respect to C. So, we get T2 T1 of u. So, the coordinates will be equal to T2 of T1 of u with respect to C. So, now we will apply first what happens to this operator T2. So, we can take out the matrix representation of T2. So, we get T2 with respect to BC times T1 of u with respect to B. So, now again we repeatedly use the same result. Now, we can take out this with respect to the matrix representation. So, then this is just T2 BC times T1 AB times the matrix representation of u with respect to A. So, on the other hand, so we will have this quantity equal to T2 composition T1, the matrix representation of this with respect to AC times the coordinates of u with respect to A. Now, this equality is true for all vector. So, this is true for all u in u. So, that means these two matrices are supposed to be equal. Okay, that is something very simple to do. So, some basic exercise is that if AV equal to BV for all V in V, where both A and B are the respective dimensional matrices. Okay. So, then that would imply that A equal to B. So, this simple fact that we are using here, and that actually implies immediately that the matrix representation of this composition is nothing but the product. So, this is indeed a very important observation, because we will be talking about group operations which will be represented as matrix multiplication. So, that means we are supposed to understand this matrix multiplication, that is composition of linear maps, very well. So, now it is immediate that, so if you take the matrix representation of some invertible linear operator, so whose inverse will be the matrix representation of the inverse of that operator. So, that means you take the matrix representation of this T, let us say T is coming from endomorphism of V, and assume that T is invertible operator. So, that means T is an element of GLV. So, if we take the inverse of this matrix representation of T with respect to the basis which is fixed for V, so then that is exactly the matrix representation of T inverse with respect to the same basis, and this easily follows from this observation. I will leave it to you to prove. Okay, as I promised before, so let us talk about the change of basis, so which is very important. So, let me just motivate, and after that I will stop, then we can actually see how to do the change of basis in the next class. So, what is the meaning of change of basis? So, let us actually go from the point of view from linear transformations. So, let us say we have a linear transformation which is defined on capital V. So, now we can actually fix a basis B and then talk about the matrix of T with respect to B. So, this is actually defined. So, now if I change the basis B to some other basis B dash, so let us call it V 1 dash etcetera V n dash. Okay. So, this is old basis which is fixed for us, and then we are changing this to new basis, let us call it B dash. So, then there is a matrix of T with respect to B dash. So, now the natural question is how they are related. So, how the matrix of T with respect to B and the matrix of T with respect to B dash are related. So, this is very important information that we require. Actually, this relation used everywhere in representation theory. So, we will understand this relation in the next class. I will stop here.